Welcome to week number 9 of ECE 111, Introduction to ECE. This week, we're going to look at topics we cover in ECE 206, Circuits 1. Now, what we looked at last week was solving one equation, one unknown for circuits. This week, we're going to generalize it, how to solve n equations for n unknowns with circuits. For that, we really need to use Matlab. Now, the concepts we're going to be covering would be Kirchhoff's current loops, Kirchhoff's voltage nodes, writing n equations for n unknowns, solving n equations for n unknowns, and that's using Matlab, then checking your answer using CircuitLab. Now the circuit I'm going to be looking at would be this one. Here I've got 4 unknown voltages, 3 unknown currents. A couple ways to solve. What we looked at last week is, can I set this up as one equation, one unknown, and then solve? And yes, you can do that. A more general solution is to set it up as n equations for n unknowns. Now with one equation, one unknown, you can use a calculator, like an HP42. For n equations, n unknowns, that's when you really need to use Matlab. So this class, in this lecture, we're going to be using Matlab fairly extensively. One thing about resistor circuits. Resistor circuits are used in electrical engineering. They're also used in mechanical engineering. Resistor circuits can model heat flow. Resistor circuits satisfy the same equations as heat flow, and both problems can be solved by writing n equations for n unknowns. For example, suppose I have a one-dimensional metal bar, like a soldering iron. I've got the base temperature, that's your heating element. The metal bar, or the soldering iron, has, using finite element models, a couple different finite elements. Each one's got a temperature. At each finite element, I lose some heat, and I have some heat flow. The basic equation is that heat in equals heat out. That's the electrical analog of current in equals current out. So if I use the analogy that voltage means temperature, current means heat flow, then resistance is the resistance to heat flow, basically how well insulating it is. Then what I get is resistors in series are the thermal conductivity between elements, and resistors to ground are the heat loss of each element. So that soldering iron can be modeled as a resistor circuit like this. The nice thing about resistor circuits is these are easier to analyze, easier to build, easier to modify, and they satisfy the same equations as temperature. So by analyzing the electric circuit, I'm also analyzing the temperature and heat flow. Now some problems we'll be looking at. When I have a circuit like this, how do you solve for the voltages in the above circuit? Which is the same problem as how do you solve for the temperatures at each point along a one-dimensional metal rod? How do you solve for the currents in the above circuit? Which is the same problem as solving for the heat flow in the metal rod. If I can solve for the voltages and or currents, I can also solve for temperatures. So the method that we'll be looking at is to do analysis, simulation, and experiment. When you take circuits 1, you'll do analysis. You write the equations for the circuit. Generally, you try to write n equations for n unknowns. Then you can solve using Matlab. Once I solve by hand, I can check my answer. I can throw the circuit into CircuitLab and simulate it and check to see are my calculations correct, at least according to CircuitLab. The real test is then when you go into the lab and build the circuit. Build the circuit, take measurements. What you measure should match up with what you simulated, should match up with what you analyzed. That's what you do in Circuits 1. In this class, we're just going to use the first two, because we don't have a lab associated with this class. Later on, you'll have a lab where you verify this in hardware. To give us something concrete to look at, let's look at this circuit. Here I've got a circuit with 4 voltage nodes, 3 current loops. The goal is to find the voltages and find the currents. The first method we're going to look at is called voltage nodes. If I just look at the node voltages, I've got node 0, 1, 2, and 3. I've got 3 unknown voltages, 4 unknown voltages. If I can write 4 equations for 4 unknowns, I can solve for the voltages. That's kind of a common trick throughout electrical computer engineering. If I can take a problem and write it as n equations, n unknowns, then I can solve. To solve, I really need to use Matlab. but Matlab excels at solving n equations for n unknowns. So the first step is to pick one of these nodes and call it ground. I'll call this node down here ground. All the voltages will then be relative to ground. The second step is write n equations for n unknowns. I've got 1, 2, 3, 4 nodes. Give me 4 equations for 4 unknowns. The first one's kind of easy. I know that b0 minus 0 equals 10, b0 equals 10. That's this equation. That one's done. Second equation, at node 1, currents have to balance. Current left plus current down plus current right equals 0. There's a couple ways to write this. You can do current in equals current out. What I prefer is all the currents from the node have to add to 0. One of them will be negative. If you don't mind negative numbers, it's not a big deal. But the nice thing is the equations are easier to write, and there's a pattern. So if I do that, the current left is b1 minus b0 over 30 plus b1 over 150 plus b1 minus b2 over 40 equals 0. Now the pattern that I mentioned is this. If you notice at node 1, all the b1s are positive. All the other terms, all the other nodes, b0 is negative, b2 is negative. That's kind of a quick way to check your answer. When you write the node equation, at node 1, all the b1s are positive, everyone else is negative. Let's go to node 2. At node 2, that's the purple ones, current left plus current down plus current right equals 0. That's b2 minus b1 over 40 plus b2 over 200 plus b2 minus b3 over 50 equals 0. Again, notice all the b2s are positive, everyone else is negative. At node 3, current left plus current down equals 0. Current left is b3 minus b2 over 50, this turn. Current down is b3 over 250. Again, all the b3s are positive, everyone else is negative. So now I've got 1, 2, 3, 4 equations for 4 unknowns. Should be able to solve. To solve, what I do is 4 equations, 4 unknowns, solve. As kind of a sidelight, I guess I kind of mentioned that. Checking for sign errors. All the b1s are positive, b2s are positive, b3s are positive. Looks good. Sign errors are really common. If your answers do not match with Circuit Lab, either your analysis is wrong or Circuit Lab is wrong. My bet is that Circuit Lab is right. So that's kind of a quick way to check for sign errors. They do happen. To solve, what I would do is group the terms. Take this guy right here, group all the b1s together, all the b0s together, all the b2s together. When I do that, I get this. b0 equals 10, first equation. At the first node, I get minus 1/30th b0. These added together. That's the 1/30th plus 1 over 150 plus 1 over 40. b1 minus 1/40th b2 equals 0. There's your first equation. And you kind of see the circuit from here. This says I've got 30 ohms between 0 and 1. I've got 40 ohms between 0 and 2. And node 1 has 3 terms, a 30 ohm, 150 ohm, and 40 ohm connected. At node 2, grouping the terms, I've got 40 ohms between 2 and 1, 50 ohms between 2 and 3, and at node 2 I've got 40, 250, 40, 250. At node 3, I've got 50 ohms between 3 and 2, 50 and 250 ohms at 3. Those are the same equations with the terms grouped. Now to solve, I put this in matrix form. Kind of arbitrarily, I'll just define the order to be B0, B1, B2, and B3. Then the first equation, B0 equals 10. 1 times B0 is 10. What I like doing is, just as a reminder, the first column is times B0, second times B1, third times B2, this is times B3. Just a reminder to myself. Second equation, minus 1/30th B0, plus this mess times B1, minus 1/40 times V2 is 0. Third equation, minus 1/40 times V1, this mess times V2, minus 1/50 times V3 is 0, and so on. Once I put it in matrix form, solve. And this is where Matlab really helps. Input the matrix into Matlab. And here, the trick I did is I ran out of space. Here's the first row. Here's the second row. And I run out of space. So terminate it. Next, I'll take the previous answer, the last two rows, add to it, the third row, and the fourth row. Just somehow get that into Matlab. The B matrix, this guy right here, is 10, 0, 0, 0. So that's 10, 0, 0, 0, 0. Then the voltage is just the inverse of A times B. There's my voltages. Okay, Matlab will solve n equations for n unknowns really, really well. Next, I'd like to check my answer. A good way to check your answer is to go to Circuit Lab. We use Circuit Lab. There's many others. Circuit Lab is just darn friendly. It's really cheap too, 24 bucks a year. Really cheap for students because you get it for free. Take the circuit, input it in Circuit Lab, just like we did last week. Drag and drop the voltage source, the resistors, double click to change the value. Connect up all the components, put the labels on the voltage nodes, then find out what's the voltage at V0, 1, 2, and 3, doing a DC analysis, and I get the same answer that I calculated in Matlab. Again, you should get the same answer. If the two do not match up, either you made a mistake or Circuit Lab made a mistake. Circuit Lab is pretty well debugged. If there's a mistake, you probably have one of the components in there wrong. A really common mistake is if I do 250 M, that's actually 250 milliohms. If I want 250 mega ohms, that'd be 250 capital M. That's a mega ohm, milliohm. There's a difference. Anyway, this matches up, so I did it right. And checking, here's what Circuit Lab gives me, here's what Matlab gives me. Same answer. Okay, so that's one way to solve. When you take circuits 1, on the tests, you don't have access to Matlab. But what you can do on the tests, what I typically do when I teach circuits 1, is ask you to write the equations. So for example, here's the circuit, give me 4 equations for 4 unknowns. On the test, that's all you would do, go on to the next. On the homework, I could then put that in matrix form, throw it in Matlab and solve. But on tests, typically you don't have that luxury. So, just as practice, let's write the node equation. I need 4 equations for 4 unknowns. First one's easy. I would say that V0 equals 10. I would start with the voltage sources. Actually, this is 10 minus 0. This difference is 10. You don't normally have to write minus 0. Next, node V1. Current left, down, and right equals 0. That'd be V1 minus V0 over 15. Current down is V1 over 200 plus V1 minus V2 over 20. That's everyone. That's got to add up to 0. Next, let's do node V2. Now, this is where instructors like myself get accused of being tricky. That's a compliment. What we try to do at the junior level is we try to set it up so you learn the concepts, we test the concepts, we try to make sure that you can't memorize your way through. This is kind of why I think the junior year is the hardest year in college. The first 2 years you can memorize your way through. In calculus, the derivative of sine is cosine. The derivative of cosine is minus sine. That's stuff you memorize. Once you get to circuits, you can't memorize every circuit. So what you might see is on the homework, I see this circuit, and you get really good at doing that circuit. On the test, I change the circuit, I add this 30 ohm resistor. Now analyze it. If you're trying to memorize your way through, you're stuck. I've never seen this circuit before, I have no idea what to do. If you're learning the concepts, it's not a big deal. At node 2, I have 4 terms. Current up, left, down, and right add to 0. The current up is V2 minus V0 over 30. The current left is V2 minus V1 over 20. Current down is V2 over 250. And the current right is V2 minus V3 over 25. That has to equal 0. And note, if you're learning the concepts, the currents have to add to 0. Not a big deal. If you're memorizing circuits, I'm stuck. I've never seen this circuit. That's kind of what we do. We try to test concepts, not memorization. And it's kind of my job as an instructor, give you a circuit you've never seen before, really trying to test. Are you trying to memorize your way through, or are you learning the concepts? The concepts always apply. The circuits always change. And likewise at node 3. The main concept you're going to see over the next 4 years is n equations, n unknowns. I almost invariably try to convert a problem into solving n equations, n unknowns. If I can write the n equations, I can solve. Likewise on the tests. I will check, can you write n equations, n unknowns? If you get the equations right, presumably you can solve using Matlab. So that's voltage nodes. Second technique is called current loops. Here the idea, if I go around any closed path, the voltages add to 0. In this case, if I look at the windows, I've got 3 windows. I can define the currents any way I like. I like making everything going clockwise. If I do that, there's a pattern that we're going to see. So let's call the 3 currents I1, I2, I3. I've got 3 unknown currents. If I can write 3 equations, I can solve 3 equations for 3 unknowns. So the first step is count the number of windows, define your currents, and the direction. The second step is write n equations for n unknowns. Around loop I1, if I go around this path, wind up where I started, all these voltages add to 0. So this voltage is minus 100, or actually minus 10, this guy right here, plus this voltage, that's I times R. I is flowing in from the left, so that's I1 times 30. Plus this voltage. That's 150 times the current going down. The current down is I1 minus I2. So plus 150, I1 minus I2, I'm back where I started, equals 0. Around loop I2. Around this loop right here, these have to add to 0. So that's 150 times the current going up. The current up is I2 minus I1. Plus 40 times the current going right, that's just I2. Plus 200 times the current going down, that's I2 minus I3. And I'm back where I started, is 0. Around loop I3, these voltages add to 0. The current up is 200 times I3 minus I2, plus 50 times I3, plus 250 times I3 equals 0. There's my 3 equations, 3 unknowns. Now the pattern that I was talking about. If you notice, around loop I1, all the I1s are positive, everyone else is negative. Around loop I2, all the I2s are positive, everyone else is negative. Around loop I3, I3s are positive, everyone else is negative. That's a quick way to check for sign errors. If this is a test in circuits 1, at this point you're done, go on to the next problem. I've got 3 equations, 3 unknowns. If it's a homework problem, I then can solve. To solve, you group the terms, put it in matrix form. So I'm going to call this guy over here I1, I2, I3. The first column is times I1, second times I2, times I3. So this equation is 180 I1 minus 150 I2 is 10. Minus 150 I1 plus 390 I2 minus 200 is 0. 200 I2 minus 200 I2 plus 500 I3 is 0. To solve, let's call this A. Let's call that B. Throw that in Matlab. Here's A. Here's B. The current then is the inverse of A times B. There's the current. And that's I1. This is I2. And this is I3. The reason they're in that order is that's how I set up my equations. To check your answer, throw it in Circuit Lab. So build this circuit. I'm going to click on this point, find the current through R1. Click on this point, find the current through R2. This point, find the current through R3. And the first one gives me I1. This gives me I2. This gives me I3. And if you notice what Circuit Lab calculates, that matches up with what Matlab calculated. That should match. Now, kind of a sidelight, there are other currents in this. Let's leave that in there. If I clicked right here, that current would tell me I2, I did that wrong. It's I1. Come on, there we go. This current right here is I1 minus I2. So I could check that in Circuit Lab, but then I have to do a little bit of calculations. What is I1 minus I2? The difference is what Circuit Lab is going to give me through R4. So it's a little bit easier if you pick a resistor where only one current is going through it. Then I don't have to do any calculations. So here's a practice problem. I've got 4 windows. Write 4 equations for 4 unknowns. Okay, let's start with I1. With I1, let's start right here at 30 ohms. I get 30 times I1, that's this voltage, coming down, plus 20, times the current going left. The current going left is I1 minus I3, plus the current through the 15 ohm resistors. 15 times the current going left, that's I1 minus I2, and I'm back where I started. That has to add to 0. There's my first equation. Second equation, around I2. If I start in the lower left corner, that's minus 10, plus 15 times the current going right, 15 times I2 minus I1, plus 200 times the current going down, I2 minus I3, and I'm back where I started, equals 0. Next equation, let's start here in the lower left corner. 200 times the current going up, this I3 minus I2, plus 20 times the current going right, I3 minus I1, plus 250 times the current going down, I3 minus I4 equals 0. And finally, start in the lower left corner, 250 times the current going up, I4 minus I3, plus 25 times I4, plus 300 times I4 is 0. 4 equations for unknowns. Now as a check, around loop I1, all the I1s are positive, everyone else is negative. Around loop I2, all the I2s are positive, everyone else is negative. I3, 3s are positive, everyone else is negative. I4. Also check the units. I times R, volts plus volts plus volts equals 0. Volts plus volts plus volts equals 0. If you had an equation like this, there's a mistake. I've got volts plus amps. Right away you know there's something wrong. I need that 200 ohms. If I had this, that's a problem. Volts plus ohms. That's nonsense. I need to have the same unit for the equations to make sense. Quick way to check your answers. Now, how you solve these problems kind of changes over the years. Back when I was in college, solving 4 equations for 4 unknowns was just a pain. So you do any trick you could to come up with 2 equations, 2 unknowns, or 1 equation, 1 unknown. Today, I don't really care. Give me 20 equations, 20 unknowns. I can solve that really easy. Just throw it in Matlab. With Matlab, the number of equations really don't matter. What matters is get the equations right. That's going to show up when you take circuits 1, circuits 2. The tests typically test, can you get the equations right? Get the equations right, presumably you can solve using Matlab. But what really matters is get the equations right. Finally, let's look at 10-stage RC circuit. That's 10 equations, 10 unknowns. Now this could be kind of annoying, but if you notice there's symmetry, all these are 1 ohms, all these are 100 ohms. So because of that, the first 9 nodes have the same equation. But take node number 5, for example. Right here, current left, current down, current right equals 0. Current left is V5 minus V4 over 1. Current right, V5 minus V6 over 1. Current down, V5 over 100. Plug in numbers. That's the equation at node 5. All the nodes are going to be the same equation, just change the index. The oddball is node number 10, because there's only 2 resistors attached. At node 10, this term goes away. So we just have V10 minus V9 over 1 plus V10 over 100 equals 0. That's my last equation. In Matlab, I can solve. I'm going to have some big 10 by 10 matrix times voltage is a 10 by 1 matrix. Almost all the elements are zeros. Notice over here, all the terms are 0 except the 2 neighbors and itself. In node 5, I've got 2.01 times V5. At node 4, 2.01 times V4. So the diagonal is 2.01, off diagonal is 1. I can do that in Matlab. Start out with a 10 by 10 matrix of zeros. Most things are zeros. Along the diagonal, all the diagonal terms are 2.01. Off diagonal terms are minus 1. Oddball term is number 10. 10, 10 is 1.01. This is now your A matrix. Again, not that bad to input, mainly because almost everything is 0, and there's a lot of symmetry. The B matrix is just 10, 0, 0, 0, 0. I think. 100, 0, 0, 0, 0. Then the inverse of A times B are the voltages. So there I just solved 10 equations, 10 unknowns. With Matlab, really easy. By hand, really painful. So we would not ask this question back in 1970. Now, sure, why not? Just write the equations, let Matlab do the work for you. If I plot the voltages versus node, this is kind of like the temperature along a metal bar. If this is a soldering iron, heat up the left side to 100 degrees Celsius. As I move along the bar, it's going to cool down, and the tip will actually be about 62 degrees Celsius. So that's kind of solving circuits using voltage nodes, current loops. And the later part of circuits 1, the beginning part is just resistors, conservation current, conservation voltage. You try to solve circuits with 1 equation, 1 unknown. With that, I can do resistors in series, resistors in parallel, stuff like that. Later on, you get more complicated circuits. For the more complicated circuits, I've got 2 tools to play with. I've got current loops and voltage nodes. In both cases, I'm trying to write n equations for n unknowns. With current loops, I define the current loops and sum the voltages around n closed paths, write n equations, n unknowns, then solve. With voltage nodes, I take n voltage nodes, sum the currents from the node to 0. Then at n nodes, n set of equations, I get n equations, n unknowns. Once I have n equations, n unknowns, I solve. Just put in matrix form and solve in Matlab. Now, one kind of comment. There are ways to do this wrong. For example, back up here, if I want to do current loops, I need 3 equations, 3 unknowns. I could say, here's the first loop. That's one equation. Here's the second loop. Here's the third loop. That doesn't work. In Matlab, if I did that, I'd get 3 equations, 3 unknowns. When I solve, I get matrix not invertible. If you get an error in Matlab, what it's trying to tell you, well, that's the problem. If you get an error, the math is trying to tell you something. The challenge is trying to figure out what the math is trying to tell you. What it's telling you is I don't have 3 independent equations. I just copied the same equation twice. Writing the same equation 3 times doesn't give you 3 times the information. It's just redundant. If you get a divide by 0 or matrix not invertible, I did a mistake like this. Instead, I need to say, here's 1 equation, here's 2 equations, here's 3 equations. Then it does work. And there's actually multiple solutions. I could actually do this. Here's 1 equation, 2 equations, here's 3 equations. That also works. What I cannot do is I can't say here's 1 equation, here's 2 equations, here's 3 equations. That's redundant. Again, I get matrix not invertible. For voltage nodes, I can get the same problem. On this one, I need 4 equations, 4 unknowns. If I were to say, this is 10, here's my second equation, let's write it again, I'll get matrix not invertible. Again, what the math is trying to tell you is you didn't write 4 independent equations, you just copied one of them. There's a thing called a supernode. I can form a closed path. And what I'm really doing here is saying that here is a closed surface. The current out of that closed surface has to add a 0. That's not the only closed surface I could use. I could do this as a closed surface. That's called a supernode. For a supernode, these currents have to add a 0. And that's everyone. If I say, let's do B0, B1, B2, in the supernode, I get matrix not invertible. Again, that's telling me that I don't have 4 independent equations. I copied one of them. I repeated one. I need this 4th equation. So again, when you're doing voltage nodes, if you're getting divide by 0 error, the math is trying to tell you something. It's saying you don't have the equations correct. You copied an equation. You're missing one. Trying to figure out what the math is trying to tell you, that's the challenge. But anyway, that is week number 9 for ECE 111. Some of the things we'll be doing when you take later on courses is trying to set up n equations and unknowns. So the reason you're covering that, the reason we're beating that into you, is this is a really common technique. This is a really powerful technique, really useful technique. I can solve all sorts of problems with n equations and unknowns. I can solve for currents, I can solve for voltages. And with Matlab, I don't really care how many equations I have. All I really care is get the equations right. So that's week number 9 for ECE 111.